So we are already recording. Let me start then. First of all, I'd like to thank all the committee members, which is formed by Professor Luis Alberto. Let me put the full name here. I have here. Professor Luis Fernando Costa Alberto, he's from University of São Paulo, campus in São Carlos. Professor João Alberto Passos Filho from the Federal University of Juiz de Fora in the Minas Gerais state. Professor Joe Chow from Rensselaer Polytechnic Institute in Troy, New York. Professor Murilo Eduardo Casteroba Bento from COPE, UFRJ. I thank you all for accepting this. For the Alain, he will be Alain Ferreira. He was supervised by myself. I am Glauco Taranto from the Federal University of Rio de Janeiro, and Dr. Tatiana Assis, that used to be professor also here, but now she's in National Grid, is ESO in UK. So we will start with Alan. He will have about 50 minutes or something like that for the presentation. Then we will go for I open for the committee members to argue with the candidate. So without further ado, I will pass to Alan, and I would say I will not expect you to have your videos on, and Alan is speaking, but I would like you to open your video when you are going to argue the candidate. So feel free to leave your camera open or close, no problem. Alan, the floor is yours now.
Hello, good afternoon, everyone. Can you hear me well?
Yeah, we can hear, but we are not seeing in the showing the presentation mode.
Okay.
The slides.
Is it on the presentation mode now?
Now you have to go to display settings.
Okay.
Go to display. No. Go to display settings. Up.
Okay.
Go there. Click.
Here.
Click in display settings and put I think it's double, because
okay.
Alan, you have to switch your screen because you are now showing the one for the
okay. Second. Sorry for that. Okay. Is it better now or same thing?
Okay, now it's okay.
Now it's okay.
Now it's okay.
Now it's okay. Okay.
Yeah. Yeah.
Okay.
Now it's okay.
Okay.
Go ahead.
Okay. So first of all, I'd like to give good afternoon for everyone. My name is Alain Ferreira. I'm here today to present the developments of my thesis. And before I start, I'd like to thank everyone in the audience that take the time to be here today. And a special thanks to my doctoral committee, Professors Glauco Taranto, Tatiana Assis, my advisors, as well as Professors João Filho, Luis Alberto, Murilo Bento, and Professor Joe Chow. Thank you so much for accepting to be here today. So without further ado, let's get started. So the title of my work is New Adaptive Method based on Synchrophasors and Insights on Network Equivalence for long-term voltage stability assessment, right? This is our schedule for today. So basically, I have divided my presentation for today in basically 4 parts, basically in 4 main parts. Okay, so the beginning, I'm gonna give some brief introduction about the main subject of this work, which is regarding voltage stability, right? After that, I'm gonna present the extended adaptive approaches that we have developed in the scope of this work. Basically, in this part here, I'm gonna show how we have improved the original adaptive approach, right? After that, I'm gonna give some insights on network equivalence using the Thevenin theorem, okay? And finally, I'm gonna share some conclusions and some ideas for future works, okay? So let's get into the introduction part, okay? So to start, it's important to remind the relationship between voltage stability and maximum power transfer, because this concept will be very important when we think about monitoring the issue of voltage stability in power systems. And just to be clear about what types of evaluations we're going to be doing today, we're going to be interested in assessing voltage stability in a long-term perspective, regardless if the disturbance is large or small, right? But it is timely to mention that the analysis presented here may also be applicable for short-term voltage stabilities. But what is interesting to mention is that it was not the focus of this work, okay? So as voltage stability is the one of the main subjects here, what we can find from a IEEE paper about classification and definition of stability in power systems. This definition presented here in the screen, which basically can be divided into main parts. The red part basically says about what a stable system behaves when there is a disturbance regarding the voltage stability. So it says that when the system is subject to a disturbance, if the system is voltage stable, it need to cap the voltages throughout the system in a specific range of values, right? But this definition also informs us what this stability will depend on, okay? And basically will give us a very important hint on how to monitor the voltage stability in power system, which is, we have here in the final part that says that the ability of the power system to keep stable is constrained by the maximum power transfer to a specific set of buses, right? So what we see here is that in practice, the voltage stability limit of a power system is highly related to the maximum power transfer to specific set of buses. So we can take advantage of that in order to monitor the voltage stability in power system. Okay, but how to do that? How to predict? How could be possible to predict the voltage stability of power system? Just from the definition you just saw, we see that there is a high correlation between voltage stability and maximum power transfer to a set of buses in the power system. So because of that, we can use the maximum power transfer theorem to do that task and estimate the voltage stability of a power system of interest. Okay. So just to remind us about the maximum power, maximum power transfer theorem says, we have here a load bus connected to its Thevenin equivalent, right? And basically, the maximum power transfer says that maximum power transfer gonna happen when the absolute value of load impedance becomes equal to the absolute value of the Thevenin impedance, right? And in this way, we find a very good way to monitor the voltage stability of the power system. Okay, and we can say that this theorem, maximum power transfer theorem, will be the foundation for the Thevenin-based methods when we are aiming to assess voltage stability, right? So because of that, we can share that around the methods that we find in the literature, they share a basic operation mode, okay? Which is, first, they aim to estimate the ZTH and ZL from PMU measurements, right? The idea then is to update this estimation as fast as possible in order to track any topology changes that may happen in the system, right? And having both impedances, ZTH and ZL, through the impedance matching criteria, okay, we can monitor the power, the stability of a power system in terms of voltage, right? But as the impedances do not have a straight relationship with how much power we still have in the power system, we have some power margin indexes in the literature that are based on those Thevenin parameters, and using one of those strategies, we can then monitor the stability in a power system. As well, as we understand that the monitoring of voltage stability is rightly dependent of the accuracy of the estimated method, we can mention as well that if an approach inaccurate estimates those parameters, it may lead to wrong estimations of the voltage stability limit of a power system, right? And this can be one of the reasons that some methods may not work properly. So what is happening actually is that they are not properly estimate the equivalent impedance, right? Okay, so here we can organize the methods inspired on Thevenin equivalent and PMU measurements in these two big families. That is methods based on PMUs and topology knowledge, and methods just relying on PMUs. And just to make sure we emphasize the methods we are mainly evaluating this work, we're going to be interested about the adaptive methods, right? Because of that, it is important to understand reasonably its operation mode, okay? And starting again from, okay, let me take the laser. Starting again from the case where we have a load bus connected to its Thevenin equivalent, it is possible to define those quantities present in this circuit in this way. And here it's interesting to highlight that in this way we are solving the problem. We have set the load current as the reference phasor, right? And beta here, which is one of the quantities that we are evaluating as well, is the angle of the equivalent voltage of the system. Okay, so what is our goal in adaptive method? Basically, we aim to describe ETH and ZTH, the equivalent parameters, in terms of VL and IL, which are the PMU measurements phasors. Okay, and to do that, we can apply Kirchhoff voltage law in this circuit, separate this complex equation into real and imaginary parts, neglecting here the resistive part of the Thevenin impedance, because we are thinking about transmission networks, okay? So this system of equation that we have this analysis here. We have three unknowns, which basically are the Thevenin parameters that we are wanting to obtain, wanting to estimate, and only two equations. Thus, we have here underdetermined system, right? But this situation that was a problem became a solution because from this issue, the adaptive approaches arise, okay? So basically, if we set one of the unknown variables, for example, XTH, that we are calling here as free variable, right? We are able to compute the other ones. So to solve this system of equation, if we set XTH as free variable, we can compute beta and ETH, okay? Alternatively, we can also set ETH as a free variable. And then we're going to have what we're calling here as adaptive ETH approach. And in this case, the quantities that they're going to be computed going to be beta and XTH, right? And the issue is this. The free variable is the specified quantity. And what we have is that if it is possible to specify this free variable as the actual value, what we have is that the other parameters are going to be also known. Okay? And from this, we can organize the adaptive approaches in this way. First, we have to set one of the quantities to be the free variable, ETH or XTH. But just setting this variable do not solve the problem, because we still do not know the actual values for the free variable. Okay, so the idea is that we have an updating scheme, which in this case we have our scheme is adaptive in order to bring the free variable initial guessing towards its actual value, because in this way the other quantities going to be converged as well. And in our case, because we are using PMO measurements to drive the updates of the free variable, we are calling here we are giving here the adaptive concept to this approach. Okay, so when we talk about adaptive approach, it brings this concept is related, sorry, to the use of PMO measurements to update the free variable for every time window of PMO measurements, right? The first time Thevenin parameters was estimated this way. It was in 2008 by Quartz and Toronto. Okay, and in that occasion, the authors have developed the adaptive ETH approach, that is setting ETH as a free variable and then computing beta and XTH. Okay, and to drive the updating process, the authors in that occasion have developed a theorem based on the comparison of delta ZL and delta XTH for each two consecutive PMO measurements. Okay, so basically they have for each two consecutive PMO measurements, they compute delta ZL, which is the variation of the load impedance, and delta XTH, which is the variation of the estimated Thevenin reactance. Okay, and based on those two quantities, they set its algorithm. Okay, and just to comment here, what is the rationale of this method? We can say that basically, if delta XTH and delta ZL have variations in the same direction, it means that the estimated ETH for that time window is overestimated. So the action that should be taken that time window should be decrease the estimated value. Okay. Conversely, if delta XTH and delta ZL have variations in different directions, it means we have underestimated ETH. Okay, and the action to be taken that time window should be to increase the estimated value. However, if one of the variations is equal to 0, the method should not update. And it is important to bring the physical meaning of these variations going equal to 0, because we're going to use one of them to develop the extended approach further. Okay, so basically, when we have delta ZL equal to 0, it means that the load of the system did not vary in that time window. So in this case, we should not update. But when delta XTH is equal to 0, it means the method have converged. Okay, so when delta XTH is equal to 0, ETH have reached its actual value. Okay, this green line here. Okay, so it's important to keep in mind those ideas. Okay, however, after a deep evaluation of the original ETH adaptive approach, we found out that the methods in some cases may diverge the estimation. Okay, one of the problematic situations is when power factor changes between the two considered measurements. Okay, so just to show an example of this, we have here this system, okay, a load bus, and for this case, the actual Thevenin parameters are ETH 1 per unit, XTH 0.1 per unit. Okay, and what we're gonna do here is to subject this load to a variation. Okay, so here we have ZL1, okay, and ZL2, which are the load impedances for two consecutive measurements. And here we have analyzed two cases. The actual ETH is equal to 1 per unit, but here I'm guessing a value a little bit higher, okay? That is overestimated value. When we compute delta XTH and delta ZL, the method should properly update. But what we see here is that we have overestimated ETH, and according to the algorithm, if delta XTH and delta ZL have variations in different directions, it should mean that the estimation is underestimated and not overestimated. So in this case, when we do this variation, we are doing this variation with variation of power factor. And in those cases, we see that wrong updates should be given to our estimated value. And we may think that if you have many time windows with wrong direction updates, we see that the estimated Thevenin voltage would diverge, right? A similar case happened to when we set underestimated value here. Okay, the comparison delta XTH delta ZL did not provide correct updates. Okay, the second case where the current approach fails is when we have capacitive loads, because we have checked that in some loading scenarios, ETH may lag the current phasor IL. So it means that beta should be negative. But when we see the formulation that computes beta, it is an even function, right? So it's not possible to compute negative betas when the actual beta is negative, right? And again, if you use the wrong beta to compute XTH, you're gonna compare delta XTH with ZL, will give again wrong updates, and it can make the method estimation diverge as well. Okay, so in order to find a way to bridge those gaps, in order to bridge it, to solve those gaps, some improved approaches were developed, right? And here we are going into the explanation about the extended adaptive approach. The first one we are calling here extended adaptive method. In this approach, what we do here is to set again ETH as a free variable, but now what drives the updates of the free variable is the minimization of delta XTH criteria, right? So in this case, we only use delta XTH to define if we're going to increase or decrease for each time window evaluated. Okay, so here we have an example, brief example of that. So this is the case where the original approach had failed. Okay, we have just talked about that, and talking about the overestimated case using the new concept. Okay, so we have this as the guessed value, 1.0001. Okay, delta ETH here is the increment to be set, to be given to this guessed value. So what we're gonna do here is to think, if we decrement ETH, we're gonna have this value here. If we increment ETH, you're gonna have this value here in the bottom. Okay. So what we do now is to compute the absolute value of delta XTH. And what we see here is that we should actually choose for the first option to decrease, because the decreasing of the current estimated value gives us the smaller delta XTH value. So we see that we do that for the further time windows. We're going to have the convergence of the method very well, much more in a much more effective way. So this is what we are calling here the minimization of delta XTH. For each 2 consecutive PMO measurements, okay, we're going to do this evaluation and update the free variable accordingly. Okay. The second issue that we had in the original approach was regarding the negative value of beta. Okay, so because again, our cosine is an even function, it's not possible to compute negative values when beta is actually negative. Okay, so to solve that, we had to develop an algorithm to, in real time, for each 2 consecutive PMO measurements as well, to distinguish when beta is negative or positive. And the idea behind our method, our algorithm to estimate the sign of beta is this. We can think here again in the load bus connected to its Thevenin equivalent. And if we see from the perspective of the voltage source, equivalent voltage source is ETH, we can define this total impedance here. Okay, so our total gonna be only the resistance of the load, but regarding the total reactance, we're gonna have the contribution of the Thevenin reactance plus the reactance from the load, right? And the idea behind of this concept is that when X total is larger than 0, that is positive, it means that we're gonna have an equivalent inductive circuit, and an equivalent inductive circuit means that ETH leads the current IL. Okay, so and basically we're gonna see these in 2 situations. When the load is inductive, right? XL is always positive because it is inductive, and we're gonna have this phasor diagram here, and always we're gonna have beta being positive for inductive loads. But when we have capacitive loads, it will depend on the situation. Okay, but basically we see that if the absolute value of XL is smaller than XTH, this is going to happen, and we're going to have positive beta. And in which occasions we're going to have negative betas. So when we have a capacitive load and the absolute value of XL is larger than the absolute value of XTH, so this sum here gonna gives us a negative value. So it means that the equivalent voltage is seeing equivalent capacitive load. So it means that we are on the situation here in this phasor diagram where ETH is lag regarding the current. Okay, and because of a matter of time, I won't go deep in that, but it was the basic to describe an algorithm to detect the sign of beta for each 2 measurements. Okay, so finally we have here the algorithm for the new approach. So basically, first of all, for every 2 consecutive measurements, you're going to check the sign of beta, whether it is positive, whether it's negative. If you have an initial guessing, you're going to consider that the initial ETH being equal to the average value, a maximum and a minimum value. Okay, and the idea here is to compute a delta XTH plus, in which we increase ETH, compute delta XTH negative, in which I decrease the estimated ETH, and check these conditions. So basically, if we have delta XTH plus larger than delta xth minus, it means that we're gonna choose. These conditions are contrary here. So if delta xth plus is larger than delta xth minus, we should pick ETH minus, right? So I'm sorry for that. There is a typo here. Otherwise, if you have xth plus smaller than delta xth minus, we're gonna choose ETH plus, okay? And in case we do not have variations, we want updating that time window, right? And after we have set the new value for ETH, we update the beta value and the xth value, and the loop continues, right? So basically, this is the structure of the new extended adaptive approach. Okay, the second approach now we are calling here adaptive xth approach, and now the free variable chosen was the reactance, Thevenin reactance xth. Okay, and now in order to drive the updates for the free variable, okay, we're gonna use some developed derived sensitivity equations, right? So again, using this new scheme of operation, we're gonna be able to improve the power factor variation cases that we had issues in the original approach, and because another issue was the computation of negative beta, because xth is set as the free variable, beta is computed using the arctangent function, which has not problems to compute negative values. So we can see that this strategy is able as well to solve all the problems that we had in the original approach. And just to comment a little bit about how we have derived the sensitivity equation, okay? We start again from the underdetermined system that we had previously, 3 unknowns, 2 equations. If we replace into this equation xth in terms of the sensitivity parameter delta xth, okay, and solve this equation, this new equation for delta xth, what we obtain here is this equation that we are calling here xth sensitivity equation, right? Where basically we're gonna have some key quantities to pay attention. So what we see here, what is the idea here behind is that delta xth, okay, this quantity here is the estimated error of the estimated Thevenin reactance, right? We have here delta ETH. Okay, just a second. We have here delta ETHI, which is the variation of ETH, estimated ETH, and we have here delta QS, which is the variation of the reactive power from the source, the equivalent voltage source, right? What is important to pay attention about this equation here is that what is able to switch the sign of the increment, that is to have a positive increment or negative increment. And when we look this sensitivity equation, we see that the quantities that are able to do that are the variations of estimated ETH and variations of reactive power from the voltage source. Okay, in this way we can use those 2 quantities to drive the updates of the estimated Thevenin reactance for each 2 consecutive peer measurements as well. Okay, so we have derived the sensitivity equations, but from that we're just going to use delta ETH and delta QS and have a similar theorem that was used in the original approach, but instead of comparing delta xth with delta ZL here, we are comparing delta ETH and delta QS, okay? And for the increment, we're gonna set an increment value that we are calling here delta XTH, and using the sensitivity equation, we're going to set the direction of increment, and using these predefined the increment, you're going to update in that direction. So basically, this is the idea. And we have here the algorithm, which is basically has this operation mode. Okay, so basically, we see that if we have delta ETH and delta QS varying in the same direction, it means we need to increase the estimated XTH. However, if we have delta XTH, delta ETH, and delta QS in different directions, we need to decrease. So this is the use of the sensitivity equation going to be used in the sense to define the direction of increment. Okay, and if we check that if XTH computed in 2 consecutive measurements are equal, it means that convergence was reached. Okay, so in order to show a case example where those methods were tested, right? We have here the IEEE 39 bus system, and the idea here is to check the voltage stability performance of those methods. And basically, what happens in this system? We have the load at bus 8 here, right, which is increased until maximum power transfer is reached. Okay, and what happens in the interim is that some overexcitation limiters from generators 2 and 3 gonna act. Okay, and this situation gonna change a little bit the dynamic of the estimation of the system. And from that disturbance case, okay, we have here the estimations obtained. So first, we can mention here in the left picture, okay, we have the plot of the estimated Thevenin reactance from both methods. So the sensitivity, using the sensitivity equations in black, using the minimization process in blue, okay, and in green here we have the load impedance, right? And we can see that our methods have properly updated their values when the overexcitation limiters of the generators act. So here, about 60 seconds, generator 2 act is overexcitation limiter, and properly the estimated reactance increased. And again, when the generator 3 acts its overexcitation limiter, so we can see that the methods were able to adapt accordingly and in a proper way regarding the disturbance what's happening in the system. And we can see here that maximum power transfer happens in a very close moment from the impedance matching between ZL and the estimated value. Okay, you can see that as well if we plot here the power margin indexes. Okay, so here we have at the beginning a very large power margin. Okay, but as the system starts to be disturbed with load increasing and action of overexcitation limiters, the natural tendency is that a margin would decrease. And what we can see here is that the methods correctly can track that. Okay. Okay, have analyzed the extended adaptive approaches. We're gonna get into the discussion about network equivalence using Thevenin theorem, right? And basically the issue is this, okay? So in the literature, one can find some papers stating that Thevenin-based approaches cannot be employed for voltage stability assessment in power systems, because they say in a correct way that the Thevenin theorem relies on the system linearity, right? And usually the major claim of them is that those approaches are not able to correctly represent the nonlinearities caused by parallel loads in the system. Okay. Okay, they use usually this term parallel loads to say that there are loads in other buses in the system. Okay, but what we see, however, is that those methods based on Thevenin equivalent, okay, they were tested in many system conditions and have shown very accurate performance in detecting voltage instability on unsettling power systems. So the idea of this work is investigate a little bit what is happening. Okay, but before we go ahead in this sense, it is important to clarify some concepts that we're going to be talking about. For example, when we talk about computing Thevenin equivalent from a specific load Bayesian system, we expect to have this an equivalent structure like this that usually we call single port circuit, right? So this is what we expect when we talk about Thevenin equivalent. But here it is interesting to distinguish Thevenin equivalent and actual single port equivalent, because when we talk about Thevenin equivalent, it means that those parameters are strictly computed using the Thevenin theorem from the linear theory. Okay, and when we say about actual single port circuit, what we are saying here is that it's possible to have a single port equivalent circuit that accurately represents the external system connected to a given bus, right? And to start our analysis, is important to consider to think that those parameters can be different. Okay, so this is one important starting point. Okay, but what should be the actual single port circuit? When we think about that, we can go to the book, The Analysis of Linear Circuits from Charles Close, that says that two circuits are said to be equivalent when they cannot be distinguished by voltage and current measurements made at the accessible terminals. So what we have here is that regardless, we are using a single port equivalent, regardless this load is connected to original system, what we can say is that two circuits are equivalent if they are able to provide the same or very similar voltage and current measurements at the accessible terminals when the load is varying. Okay, and a consequence from this point of view is that real and reactive power responses should be equal as well, or at least similar, at the accessible terminals for both system, equivalent or original. So when we think about actual single port equivalent circuit, we can think about this idea that I have shared here. Okay, and thus the objective of this work is to clarify that indeed the Thevenin equivalent loses validity in representing the actual single port equivalent circuit, ZEC, seen from buses in power system, which is basically because of the power system nonlinearities. Okay, and secondly, our second idea is to show that Thevenin-based methods relying on PMO measurements can accurately assess voltage stability in power systems, since they are able to compute the actual single port equivalent parameters and not the parameters obtained using the Thevenin theorem. So the idea is to clarify those points and to demonstrate that the following system is going to be considered. Okay, so here we have this system that I'm calling generator to load system, which is one of the systems used in one of the papers going against Thevenin-based method. Okay, so here we have two loads connected here and two transmission lines, Z1 and Z2, and it is an interesting system because it has no problem to compute the equivalent by Thevenin theorem from the bus number 1. So basically, what we have here is that the impedance Z2 going to be in series with the equivalent impedance from Z1 parallel con ZL2. Okay. So according to Thevenin theorem, it should be the equivalent impedance from bus number 1. Okay. And what we have done, we have think about many possibilities of load variations in this system. And the first one that we are calling here case number 1, we consider that both loads are linear, that is Z constant type, impedance constant type. Okay, and we have chosen to increase only the demand from the load L1 and keeping the demand from load L2 fixed. And what we obtain here is that when we have the impedance matching criteria in the left, we see that the impedance matching happens directly at the time of maximum power transfer, actual maximum power transfer, because here the green curve is regarding the power in the system. Okay, and if we compute the power margin, we're going to check the same thing. Okay, when we compare the actual margin to the Thevenin margin here, they are the same. But if we choose a different situation where we have both loads as constant current type, that is not linear loads, okay, and we again choose to increase only the demand from load L1, okay, keeping the demand from load L2 constant. What we have here is that now the impedance matching time is not the same time the maximum power transfer happened. Okay, so we see here a different behavior, which is also shown here when we compute the power margins. So basically, when the actual power margin run out, the estimation would say that we still have some power to be used. Okay, so here we have the first difference that we found, and this fact can be also computed or verified using this concept here that we are calling reactive power response factor, which basically it measures the reactive power response factor from the original grid and from the equivalent grid. And the idea is that if the parameters are accurate, they should be equal or very similar. So when we compute that for the linear load case, again, we have reactive power responses very similar. Okay, but when we have the non-linear loads in the system, these reactive power responses start to be different. Okay, we have tested this case for many other impedance configurations. Okay, and here we have an interesting plotting, because here is the impedance of the load ZL2, okay, the intermediate load here, when that load was not changed, the demand. Okay, so basically what we see here is that when the load is not linear, okay, basically regardless if we are changing the demand or not, when the voltage change in the system, that the impedance of that load gonna change, and then it's not possible to keep impedances, the impedance of those cases constant if the load is not linear. Okay, so from this we have these preliminary analysis. So loads that can vary their impedances as a function of the applied voltage, that is, restore their power part or totally, it will affect the actual single part equivalent parameters. Okay, the computation of the actual single part parameters. And because of that, we see that Thevenin parameters are only valid for voltage stability assessment when it is performed in a load bus, and all loads in the rest of the system remain with their impedance constant during the loadability of that buses, which we can say that is an unfeasible condition to real energy systems, right? And thus, in general, Thevenin impedance cannot represent the actual equivalent impedance seen from a load bus, which means basically that in real power systems, ZTH, the impedance computed by Thevenin theorem, is different from the actual impedance, the actual equivalent impedance. Consequently, because they are different, so now if we use the maximum power transfer theorem to estimate the power margin, it will not happen more when those impedances match. Okay, but from these scenarios, a question may arise. So if Thevenin equivalent is not does not represent the actual equivalent from the system, what should be the correct values for the actual single port equivalent circuit? Okay, so in order to obtain that information, we have to start from a circuit theorem that do not rely on circuit linearities, and for that task we can use the intelligence theorem. Okay, that from the developments of this paper here, the authors have derived this equation that says that the equivalent impedance seen from a given bus I can be computed from the variation of the load voltage in terms of the variation of the load current, right? And in order to check how this equation would be in terms of the system impedances, what I have done was to replace into that the system impedances. I have obtained this impedance here that I'm calling the analytical model, which basically should be the actual value of the equivalent impedance seen from bus number 1 here. Okay, and an interesting fact from this equation is that here, just to clarify, K and K minus 1 are the two consecutive measurements that we are considering. Okay, and an interesting fact here is that if we consider ZL2 K and ZL2 K minus 1 being equal, that is not varying, we're gonna fall into the linear case. Okay, the equivalent impedance, the system impedance cannot vary, and this is the same equivalent impedance obtained from Thevenin theorem. Okay, so what we can see is that the linear model, the Thevenin theorem, is a special case of this general case for for non-linear loads, right? And just to finalize regarding the simulations here, in order to show that Thevenin-based methods can correctly estimate maximum power transfer for cases Thevenin theorem was not able to do, we can see here a case that we have chosen where both loads are nonlinear and both loads are increasing their demands. Okay, and what we see here is that we have, I have considered here two methods, the adaptive methods, which is the original adaptive method I have mentioned earlier, and the CPM equivalent, which is a method based on extended ward equivalent. Okay, and what we see here is that both methods correctly estimates the maximum power transfer, as well as the analytical model, because both approaches follows the analytical impedance. Okay, differently from the Thevenin impedance in the bottom part here in the dashed curve. Okay, and it was possible to check that computing the reactive power factor response as well. Okay. So, going to the conclusions of my work regarding the developed methods, we see that the developed approaches have shown improvements regarding the original approach, because now they are able to accurately estimate the single port equivalent circuit, regardless inductive or capacitive PMO measurements, that is, which means that it's able to properly update regardless of the quadrant the PMO measurement is, okay? Another improvement of the developed approaches was that both approaches were able to estimate both sides regarding a boundary bus using the same disturbance data, okay, which is also an improvement regarding the famous recursive least square method. Unfortunately, because of a matter of time, it was not possible to show this, but we can clarify that in the arguing part. The second conclusion, consequently, because our approach accurate compute the equivalent parameters, when we use indexes based on that, both indexes used were able to accurately estimate the voltage stability limit, right? And a comment here, because we have seen that our methods were tested for cases where over-excitation limiters have acted, we can say as well as that our methods are able to correctly estimate for limiting induced bifurcation scenarios, with the cases where the action of the control actions play an important role in an anticipation of the voltage instability point. Okay. Regarding the Thevenin equivalent for voltage stability assessment, what we can say is that it was verified that the power system nonlinearities affect the actual single port equivalent circuit parameters, ZEC and EEC, but the Thevenin theorem parameters, ZTH and ETH, is not able to track the impact of those nonlinearities on their estimated values, which will cause wrong estimations of voltage stability limit of the system. So, because of that, Thevenin equivalent is not recommended for voltage stability assessment purposes. The explanation why the methods inspired on the Thevenin equivalent have worked to assess voltage stability is that those methods are able to estimate the actual single port equivalent circuit and not the Thevenin parameters. Okay, because they were able to extract from PMO measurements the system nonlinearities and assure very accurate, reactive, and real power responses. In this way, we can say that for voltage instability identification purposes, what matters is whether the actual impedance is approaching to the load impedance and not whether ZL is getting closer to ZTH. Consequently, we can say that the maximum power transfer theorem concerns the impedance matching between ZL and Z equivalent, taking into account all the nonlinearities and not regarding ZL and ZTH. Okay, and finally, we can see that the analytical model was important to explicitly show what should be the correct expression of the equivalent impedance, which was different from the expression from Thevenin theorem. Regarding some ideas for future works, some ideas is to check the performance, the developed approaches on distribution networks and in power systems with DC transmission lines and their converters in order to check if our approaches are able to extract the impact of those converters, test the new algorithm in systems with high share of inverter-based resources. And finally, one idea is to expand the analytical model to any bus of the system. So having said that, I thank you so much for attention and apologize for the extra time.